Física, la Physics Motivation. The primary scientific goal of AEgIS is to measure directly the acceleration of antimatter in the Earth gravitational field. This measurement would represent the first direct measurement of a gravitational interaction between matter and antimatter. It would be a test of the so-called Weak Equivalence Principle. It's a cornerstone of the theory of relativity, and it states that the gravitational mass and the inertial mass are exactly the same. This was actually discovered many years ago, many centuries ago, by Galileo and Newton, and this principle is also known as the universality of free fall. And if you think it carefully, it's quite unique behavior. For example, you can see the difference with the electric field. Both fields, the electric field and gravitational fields, are proportional to the source of a field, inversely proportional to the square of the distance. But the acceleration in one case is proportional to the source of a field, of a second field, while for the gravitational field, the acceleration is constant. Does this principle hold also for antimatter? At the moment we don't know. It is worthwhile noting that antimatter was discovered about 15 years after the theory of relativity of Einstein in 1928. Then we have also a long-term goal, but first we have to achieve the first goal, and we didn't yet. So our attempt to why test the weak equivalence principle? Our attempts for a quantum theory of gravity typically result into new interactions which may violate the weak equivalence principle. Secondly, some open questions like dark matter, baryogenesis could benefit from a direct measurement. Also, some, very few indeed, studies also explicitly talk about anti-gravity. For example, one of these scientists, Chardin, tells that if matter and antimatter repel, that would explain the acceleration of the universe. I don't know if it's true, but this is one explanation. Well, most of the community believes that the weak equivalence principle will hold for antimatter, but on the other hand, a violation is not a priori excluded, and more importantly, we are experimentalists, most of us, so up to now this has not been measured yet. There were been attempts actually. The first one was in '67. They tried with positrons. 20 years later at CERN, at the Lear machine, they tried with cold antiprotons, but both 10 tests were unsuccessful because, as you know, gravitational force is much weaker than the electric and electromagnetic force, many order of magnitudes. So even the smallest magnetic or electric field, stray field, is bigger than the effect of the gravity. In 2013, actually, Alpha made a measurement and set a limit on the ratio between the gravitational and inertial mass, but it's so big that we cannot really call it a measurement. So how do you go? If you want higher precision, you go for antimatter, neutral antimatter, because neutral antimatter is not subject to static electric and magnetic field. That's how we plan to do the measurement within the AEgIS experiment at CERN. Why at CERN? At CERN is the only place, the only laboratory in the world where you can have antiprotons. They give you antiprotons, and so you need it to make antihydrogen. Of course, you need an antiproton and an antielectron or a positron. Most of you work at CERN, so surely you know LHC. You know also that this is not the only accelerator. You have a complete system. You go from the LINAC to the proton synchrotron booster to the PS and then to SPS and the exchange. That PS beam can be extracted and sent to another accelerator called AD. Actually, it's not an accelerator, it's a decelerator. The mechanism is obviously the same. The 26 GeV/C proton beam is hitting an air-cooled iridium target, and every 1 million proton you get 1 antiproton. So with an energy of about 100 MeV/C, actually higher. Then these antiprotons are injected into this machine that slow them down to 100 MeV/C, then deliver them every 100 seconds to the experiments. We have about 3×10⁷ antiproton each cycle, every 2 minutes, order of magnitude. This is the size of the AD hole. It's not that big, it's like 40 by 30 meters. Inside the ring you have experiments. At the moment there are 5 experiments on the floor. AEgIS, it's us, ATRAP, Alpha, SACUS and BASE. Alpha came out with nice measurements of the antihydrogen energy levels a few days ago in Nature. They are doing an excellent job in testing CPT. How the beam is shared? It's 8 hours sharing, so 8 hours we have one experiment, 8 hours the other, and the third one. So we work 1 week in the morning, 1 week in the afternoon, 1 week in the night. Then you stay 1 or 2 weeks out of the beam to allow all the experiments to get the beam. And we should start on Monday, the first beam would come, and we go up to November, let's say. This is our range. What else to say? This is the AEgIS experiment. We joined later, so they gave us a zone that was a test zone. It's very narrow, but okay, it was for us, and so we are using it. What is the idea? The measurement procedure, the overview. We have an antiproton beam, we trap them, then we go into the details of each step. We trap them, then we have a positron beam hitting a target, producing positronium. Then the antiproton and the positronium merge, and then they are accelerated, and they fly. And then hopefully it falls. So our goal is to measure the fall of this antihydrogen beam. It's easy to say, very difficult to make indeed. This would be the first measurement on gravitational effect on antimatter. The steps in which you do, first you have to trap antiprotons, and trapping of antiproton is something that you do routinely since decades now, and basically use electromagnetic traps. The function is simple. You use traps. They are this size more or less, electrodes made by aluminum or copper with voltages applied. You make a well, electric field well, so you are able to trap them axially. How do you trap them radially? With a magnetic field. We have a magnetic field of 5 Tesla with a superconductive magnet, and clearly you make the particle to spiraling along the beam, the magnetic field lines. This is how the trap works. Clearly, the antiproton that comes from the AD are too hot or too speedy, too fast to be used to merge them to make antihydrogen. Clearly, the probability of interaction goes higher when the two species are slower. Clearly, if they flash one close to the other very fast, the probability that they are catched one with the other is low. So you have to make them slower and slower. How do you slow down antiprotons? Because if you touch them with matter, you kill them. So we and everybody else use electrons. Electrons are matter, but the antiprotons and electrons, when they meet, they don't annihilate, because there are different species of particles. So we load the trap with electrons here. The antiprotons comes, they come with a kinetic energy of 5 MeV. It means that to catch them you would need 5 million volts trap. That's too much. The traps that are used in AD are 10 kilovolt, so you trap only antiproton that has a kinetic energy lower than 10 kilovolts, keV. So you may pass them through the grader, namely a few hundred microns of aluminum, so they are slowed down, and you are able to catch, well, let's say between 0.1% of the beam to 1% of the beam, more or less. Most of them goes away because the trap walls are too low. But some of them enter. Okay, you have to enter. They get to the end of the trap. It's this size, 30 centimeter or so. They are reflected, come back. Before they come back, you have to close the other side, and then they stay inside few seconds, let's say, or tens of seconds. So they have to pass through the electron, and they are slowed down to the same energy, environmental energy of electrons. That's 10 Kelvin, that's the temperature inside the trap. Once you have cooled them, you can remove the electrons with a fast kick. Every 100 seconds, every spin, we have about 10 to the 4 to 10 to the 5 cooled antiproton. Then then the antiprotons are sitting in a trap waiting. How do you make antihydrogen? Either you mix them directly, that's the way alpha and A-trap does, and the way we did it in the past. But we want to make them a beam. We prefer to use a combination with positronium. Positronium is a bound state of an electron and a positron. Then later I'll show you how we produce them. Suppose we are producing them, they fly toward the antiprotons, and then we shoot a laser to excite them. Why do you want to excite them? Because the reaction that needs to be used is this. You have protons. Well, antiproton with excited positronium gives you an excited antihydrogen releasing an electron. This is a so-called positronium charge exchange reaction. It has already been used in AD in 2004 through different positronium creation mechanism, and its advantage, the advantage is the cross-section is proportional to the 4th power of a quantum principal number of the positronium. That's why you want to excite it, so you make the cross-section higher. And then your antihydrogen is created with a well-defined quantum number, and then if you want to accelerate it, this is easier. Then, with a Stark acceleration, passing through in the same region, you have a gradient of electric field, and in this gradient you accelerate the antihydrogen half in one side and the other in the other side. This is a picture of our overall experiment. These are about 7 to 10 meters or less. We have the 5 Tesla region with one of the 2 superconducting magnets. The antiproton comes from AD here. Here on top of the AD line we have a positronium system, the positron system. In here we trap the antiprotons. Then we move them here. We move the positrons down here and create positronium here, and this is called the H production trap. Here the magnetic field is lower because you don't want to disturb the antiprotons too much. And then we have a flight region that we didn't build yet, but I will talk about that. So clearly you need good vacuum conditions to hold the antimatter, and you need a cold temperature. So the temperature inside, namely, is 4 Kelvin, but then you have electrodes and voltages, so you heat up a little bit, you come to 10 to 15 Kelvin in the production region. This is a picture of the production trap. The antiprotons are sitting in this, here. You don't see them, but the top is open or closed. Not all of them, but this half is transparent to allow the positronium to enter. The positrons are coming from here and are hitting intermittent and are hitting this target. You clearly see. And then when production is, the positronium is created, we shine perpendicular laser to produce positron. And then hopefully go down and create antihydrogen.
May we interrupt you?
Sure.
Just a question. If there is the antiproton and the positron merges, there's neutral particles, so you cannot use magnetic field to accelerate it, electric field.
No, you use electric, not a static electric field, but a gradient of electric field. So changing the electric field, there is interaction with the levels, atomic levels of the levels. I have a specific slide at the end if you want.
So
as a
even a
backup
neutral
slide.
particle can be accelerated with different electric fields.
Yes, this has been done with hydrogen. So it has been done.
Okay.
But then I have a specific slide at the end, maybe we can look it. This is the overall experiment. It's quite narrow and complicated. I don't know if you can note here the size of the space we have, for example, to plug the cables of the outer scintillators. Despite the space is really small. Now I present some results. They are not the goal or result, they are intermediate preparatory results, if you want. The first is a proof of principle that using the so-called Moiré accelerator, deflectometer, we would be able to measure the fall of the antihydrogen. We are using a classical, purely classical system. Okay, this is a purely classical system. You have, this is a measurement that Markus Oberthaler made a few years ago, and he is actually part of our experiment, and he's building the gratings and all that stuff. You have two gratings and an atomic beam that pass through it. Okay, and this system is based on geometric propagation of atomic or molecular beam, and the device is non-dispersive. The atom doesn't need to be collimated, doesn't need to be monochromatic. Basically, it's purely geometric. The illustrations show that in place of the third grating, clearly the distance between the grating has to be the same, but the intersection, geometric intersection of the tracks produces here a periodic atomic density modulation with a grating periodicity. It's purely geometrical. At the end, here, you are forming a set of fringes, nothing to do with interferometry. And the effect is the same, but it's purely classical. Clearly, you have at the maximum, at this level, are aligned with the opening, and the minimum are aligned with the solid of the gratings. If you don't have any acceleration, if the system is in accelerated motion with respect to your beam or vice versa, then clearly, suppose the force is pointing downward, then you have a shift down of your fringes, and you end up with a maximum not aligned with the opening. How they were doing it was using an atomic source with 10 to the whatever number of, clearly you have 10 to the 23 cubic centimeter of matter, so the number of atoms they could use were enormous, so they could repeat it many times in short time, were shooting, sending a lot of heat, and then were measuring with a detector the number of particles passing. Then they were moving this third grating a little bit, and then redoing a little bit, and redoing a little bit, and redoing. So they were measuring this time. But with antiprotons you cannot do it. First of all, because you have very few. We are aiming to have one or few every 100 seconds. So, very difficult. And then you cannot use a detector that we use for hydrogen. Then the idea was to replace the third grating with a position-sensitive detector able to detect the antihydrogen annihilation. Suppose these are some numbers, let's say. Suppose you are an antihydrogen beam going through, and you would, this is without any force on the antihydrogen, you would have a maximum of the antihydrogen annihilation aligned with the opening, and the minimum with the solid. Clearly you have a periodicity, so if you plot this distribution modulo grating period d, you would end up with a distribution like this, which you have a minimum aligned with the center of the solid and the maximum with the opening. This is without any acceleration, and you can measure this experimentally using also some laser to align your system to take it to also monitor the stability of your system. What about if your beam is going down? Then you will end up with a shift of the fringes. The maximum, the minimum wouldn't be in the center but slightly moved. If you do it with, if you are able to measure the time of flight between your first grating and your last detector, and the time of flight would be 2 milliseconds, so no problem measuring, then you are able to measure t. Actually, this A is what is called d here, it's grating period. So if you measure this as a function of time, you are able to measure g. So this is how...
Can I interrupt a little bit? But then you are assuming, so you said that you accelerate the hydrogen beam, the antihydrogen beam. In principle, you would prefer to have this acceleration to be very small, no? Because if it goes really fast, then the effect of gravity will be very small. You want the beam to be slow,
Yeah.
so it has a chance to fall. No?
Yes.
So
you can reach this starting with a very low, because let's say the temperature at which you have the antiproton is leading your velocity. You want them very slow. At room temperature, they would be too fast.
Okay.
Okay. Then you need to accelerate it. You accelerate it to a few hundred meters per second. This is our goal.
Okay. The smallest, the better.
The smallest, the better.
Okay.
Clearly, because it takes longer, and then the fall is bigger. The fall is of the order of few tenths of microns. And you are not able to measure it one by one, because you don't know the direction of a single antiproton, because there's a Brownian motion of every one.